Imagine you are playing a 3D open world game like GTA and you are navigating in the GTA world with your character, but on the corner of the screen you can see a 2D mini map that help you to travel, okay? And the game world is the 3D axis, that is X, Y and Z axis. So you can consider as a 3D space, that is R3 space, and the map is 2D, that is only the X and Y axis. But the position on the map still correctly represents your 3D movement, that is the movement of the character. So this is nothing but a linear transformation, that is a way to convert one space into another, like 3D to 2D, while preserving the important directional and the scaling information. So it is like folding the world smartly, not randomly. So we will first begin with the linear transformation. So we will first understand what are the functions. Okay, so I can write a function f of x equal to x square. So here function f maps whatever the input you are give into the x, okay, to x square. So I can write it like this, the mapping, that is x and f of x as 0, then 0, 1, 1. Then if the value of x is 2, then f of x is 4. If the value of x is 3, then f of x is 9, and so on. So here in this function, we are giving the input as a variable. Here x is the variable. But what if I give the input as a vector, that is x1, x2. Here the input vector maps to, for example, x1 to 3x2. So this is the vector through which the input x1, x2, the vector maps to. So suppose if I create a mapping for this, so I can write it like this: x1, x2, x1, x2. So if the input vector is 0, 0, then the f of x1, x2 is also 0, 0. If the input vector is 1, 0, then the output is -1, 0. And if the input vector is 1, 2, then the output is 1, 6, so on. So here this f of x1, x2, so this function which is taking the input as a vector is also called a vector valued function, which takes the input as a vector. But instead of this function, I can write it like this: transformation t x1 x2 as minus x1 plus x2 3x2. So here this transformation T, in this transformation T, this vector x1 x2 maps to this vector. So for example, I can say, let me draw one diagram here. For example, consider this square box as a R3 space. So it contains all the possible vector in the R3 space. And this square box as the R2 space. So this means all the possible vectors in the R2 space. And this circle is nothing but a subset of R3 space, that is a set of all possible vectors, that is subset of the vectors in the R3 space. And similarly, this is the subset B. Now, what I want is, using this transformation T, I can map the vectors of this subset, or all the possible vectors in the R3 space. For example, the vectors of this subset A to the subset B maps all the input vectors from A to the all the output vectors of the B. Okay. And similarly, I can also write transformation T. It can map all the input vectors from the R3 space to all the vectors in the R2 space. Now, I can say that this R3 space, or the subset A, is called the domain. So this means all the possible vectors, that is either in the subset A or in the R3 space, that you are giving as a input, which will be mapping to this subset B or the R2 space. Similarly, I can write this R2 space, or the subset B, is called subdomain. Sorry, not subdomain. It is codomain. So here I can say that transformation T maps all the possible vectors, that is domain, to the codomain B. So A is all the possible vectors given as an input to T, and B is a set of all possible vectors that A can map with the help of this transformation T. Now, there is one more thing. For example, if all the vectors, that is, if this transformation T maps all the vectors from subset A to only the zero vector in subset B, or R2 space, or I can say that in R2 space. Okay, so here A is domain, then the zero vector let me write it once again. So A is domain and the zero vector is called range, and the R2 space is called codomain. So for example, if you want to understand more better, so suppose A is a set of numbers 1, 2, 3, 4, and B is a set of number 1, 2, 3, 4, 5, 6, 7. Now, suppose if the transformation T map all the elements from A to B, but suppose if I give the input elements, okay, if for example the t of 1, okay, if it is, if the t of 1 maps to the element 2, t of 2 maps to element 3, t of 3 maps to element 4, then, and if t of 4 maps to element 5. So in this case here A, that is 1, 2, 3, 4, when it is given as an input to the transformation T, so it produces the output that actually maps to only this set of number only. So in this case A is called domain, then B is called subdomain, and this set of numbers that actually the transformation produced by giving this input values A, okay, so this one 2, 3, 4, 5, so this set is called range.
Oops, I said this subset B as a subdomain. My bad. So this is not subdomain, but this is codomain. So it is the space where the output lives.
So the next topic that we are going to learn is a transformation matrix. So in this case, we can understand with the help of the standard basis vector. So the standard basis vector are denoted by the I hat and j hat. So this is the standard basis vector I hat, and this is the j hat. So I can transform this vector, or I can extend this vector to any location. So for example, I am transforming I hat to, for example, this is the I hat which is transformed having the x and y component as 3, 4. That is, this is transformed. Okay, so that is T of I hat. I can mention it like this. Then this is the j hat which is transformed. Okay, so I can also write this j hat as -4 and 3. The x component is -4 and y component is 3. And I can write this vector as T of j hat, the transformed version. Okay, so the transformation, okay, the transformation matrix will be denoted by the first column will contain the x and y component of transformed I hat. So this will be 3, 4, and for the j hat it will be -4 and 3. Now using the transformation matrix, we can transform any vector, and there can be any transformation matrix. So now let me draw out a few vectors. So this is the vector A. This is the vector A. This is vector B. In the third vector is denoted by vector C. Now, if I join these three vectors, for example, from A to B and B to C, okay, so it forms a triangle. Now, these three vectors, by joining them, it forms the shape of the triangle. Now, I want to scale this triangle. So, I can use the transformation matrix. So, for example, the transformation matrix that I am used to scale this triangle is, for example, suppose it is 2, 0, 0, 2. So for example, you can consider the first column as a transformed I hat and the second column as a transformed j hat. So here vector A is denoted by 2, 0, then vector B is denoted by 0, 2, because here the x component is 0 and y component is 2, and vector c is denoted by -2, 0. Now I want to transform this triangle. Okay, so it will scale by a factor of 2. Why factor of 2? Because here the x component is 2 and y component is 2. Okay, so I can write this transformation as, I will first do it with the vector A, that is T of A. Here T is the transformation matrix. So the transformation matrix is 2, 0, 0, 2, and the vector A is denoted by 2, 0. So the shape of this matrix is 2 cross 2, and here it is 2 cross 1. So the output will be 2 cross 1 only. So it will be 4, 0. Similarly, the transformation of vector B will be 2, 0, 0, 2. That will be vector B is 0, 2. So the answer will be 0, 4. And similarly, by applying the transformation on vector C, it will be 2, 0, 0, 2. Then the vector C is -2, 0. So the answer is -4, 0. So I have got the transformation of vector A, B and C. So let's plot this vector on the same graph. So if I plot the transformation of A, that is 4, 0. So this will be this one, 4, 0. Then similarly, transformation of vector B, that is 0, 4. And the transformation of vector C is -4, 0. So similarly, if I join these vectors, okay, the transform vectors, so it still form the triangle, but it is a scaled version of the previous one, the original one. So you can understand that using the transformation matrix, you can scale the whole shape, okay, scale the vector by preserving its shape. Now here, for example, the vector A to B. So suppose if I want to find out the points lying between A to B, okay. So for example, it is denoted by Z1, vector Z1. This is B2C is denoted by vector Z2, and C2 is denoted by vector Z3. So now suppose I want to find the Z1, that is the distance between from vector A to B, okay, the number of points lying between A to B, then number of points lying between B to C, and number of points lying between C to A. So I can mention it like this. So here, let me just a moment.
Okay. Okay, fine. So I can mention z1 as vector b minus vector a, then z2, that is vector z2 as vector c minus vector b, and vector z3 as vector a minus vector c. So from this I can get a subtracting a from b, then b from c, c from a, I can get the value of z1, z2 and z3. But I want to, if I want to find the number of points lying between from a to b, then b to c and c to a, then in that case I can write the z1 as set, that is vector a plus t, then vector b minus vector a given t is between 0 to 1. So, for example, suppose the value of t is 0. So, in that case, z1, okay, the first point, that is vector a, okay, z1 equal to a. So, this is the first point, that is vector a. And now, for example, if t is 1, okay, if t is 1, in that case vector a plus vector b minus a. So in that case the remaining vector will be vector b. So it is this point, okay, the tip of this z1. So this is nothing but vector z1. So if I want to find the points, okay, so if I put the value of t that is lying between from 0 to 1, I can get the number of points on this vector z1. Similarly, for z2, I can write it as vector b plus t vector c minus vector b given 0 is less than, sorry, t is less than, t is greater than equal to 0, less than equal to 1. Similarly, for vector z3, I can write vector c plus t given vector a minus vector c given where t is greater than equal to 0, less than equal to 1. So this is how we can scale the transformation matrix. Sorry, scale the shape using the transformation matrix. So the next topic that we are going to study is linear transformation as rotation. So in this case, we will be taking this same example of this vector. Okay, so let me draw out this vector first. This is the vector A. Then this will be the vector B. and this will be the vector C. So I can write, okay, this will be the vector A, this is vector B, and this is vector C, and I will join them now. So when I join these three vectors, it becomes a triangle, and the triangle is denoted by the sides. Okay, this is vector z1, z2, and this is c3. So we have studied about these sides in the previous topic. So now the main purpose of this topic is linear transformation as rotation. Is this is a triangle, and I want to rotate this triangle by counterclockwise, that is 90 degree. So in that case I need a transformation matrix. So this is the transformation matrix: T of theta cos theta sin theta, then minus sin theta and cos theta. So I want to rotate this triangle by 90 degree and in the counterclockwise direction. So in that case the theta equal to 90 degree, or it is a pi by 2 radian. So in this case, if I substitute the value of theta, then the transformation matrix becomes T becomes, if I after substituting the value of theta, that is cos 90 becomes 0, sin 90 becomes 1, this will be minus 1, and this is 0. So this is the transformation matrix. Now I will transform each vector. Okay, so vector A, vector B, vector C. So I can write this as T of A, that is 0 1 minus 1 0, and the vector A is 2 0. So after the transformation I get the vector A as, this will be 0 and the y component will be 2. Similarly, for transformation, that is T of B, I can write this as 0 minus 1 1 0, and the vector B is denoted by 0 2. Okay, so the transformation matrix, that is transform B vector, becomes minus 2 0. Similarly, I will do the transformation for vector C. 0 1 minus 1 0. So the vector C is minus 2 0. So the transformation becomes 0 minus 2. So I got the transform value of the transform vector A, transform vector B, and transform vector C. So I am going to plot it now. So I will choose a different color for this. So the value of transform vector A is 0, 2. So I will draw the vector. This is 0, 2. Then transform vector B is 0, minus 2. This is a transform vector B. Let me draw it once again. So this is transform vectors B. Then I will draw the transformed vector C, that is 0, minus 2. Now when I join these vectors, okay, when I join these vectors, that is here A to B, then B to C. So now you can see that the original triangle get rotated by 90 degree. So this is the power of the linear transformation as a rotation. We can transform any shape using the transformation matrix. And here I can write the original vector, that is vector A, vector B and vector C as pre-image, and the vector that we get after transformed, that is transformed vector A, transform vector B, transform vector C as image. So the next topic that we are going to study is the projection. So the projection means, suppose if you are walking in a broad day sunlight, and if the sunlight is falling on you, then you can see your shadow on the ground. So that is nothing but a projection. Similarly, in case of vector, if you point out a flashlight on the vector and the shadow of that vector falls onto the some another line or vector, that is nothing but a projection. So why we need a projection? For example, you can see here the sample data set. Here each individual person has the height, weight and shoe size. So if you want to plot this data set, visualize this, so it will be a three-dimensional space. It will be in a 3D axis because it has a 3 column, that is three-dimensional features. We can call it as a this data set contains the 3 features. Okay, so now if you properly see this data set, here height, weight and shoe size are correlated. Suppose if the person is very tall, then his weight will be more, and similarly his shoe size will be larger. And if the person having the very less height, then in that case the weight will be less and the shoe size will be the smaller. So you can understand that how these columns are correlated. So with the help of projection, what we can do is we can transform the value for these 3 columns into a single column, and that column containing the value for each person will preserve the information for these 3 column, height, weight and shoe size, without losing this information. Okay, so that is nothing but a projection. With That is nothing but it is helped with it is achieved with the help of projection. So we will be studying that in the future in the machine learning algorithm called principal component analysis. Now we will study that how we are able to find out the projection. Mainly we will be studying about the formula for the projection. We will be deriving the formula. So suppose there is a vector passing through the point. Just a moment. There is a vector passing through the point 2, 1. And I can also extend this vector in the opposite direction. So this become a straight line.
Now this point from where the vector is passing, suppose this point is called the vector x, and it has the component 2 1, and suppose this line L, this line is denoted by L, so we can write L as a scaled version of vector x. Why scaled version of vector x? If I increase the value of c or decrease the value of c, I can reach at any point on this line. So that's why I have written it as a scaled version of x. Now there is another vector. So suppose this vector is denoted by vector v. Now, as I have told you earlier, suppose if there is a flashlight here, suppose if there is a sunlight here, okay, not flashlight, we have the sunlight here, and if the sunlight fall onto this vector, okay, the projection will be the straight line here. This will be the straight line, and this straight line will be perpendicular to the this line L or vector x, and this v, vector v, has a component 1 2. So the shadow of this vector v, we can denote this as a shadow of this vector v, this one starting from 0 position 0 or the origin and reaching this the point where this line ends. So this is the shadow of the vector v. Now I want to find the projection of a vector v on line L. Okay, so in that case I can write it as a projection of vector v on L is nothing but a scaled version of x. So this point, okay, this is the line, okay, or sorry, this is the vector, and we want to find this projected vector, okay, then it is nothing but a scaled version of x, as we have seen earlier that any point on this line will be a scaled version of x. So here c is the scalar. Now in order to find the projection of vector v on L, we need to find this, the value of c. So in order to find the value of c, we know that if this two line, this line and the vector x, okay, this vector x, they are orthogonal, means they are perpendicular to each other, and it forms the 90-degree here. So it forms the 90-degree with the line L or the vector x. So in that case, we know that we have studied in the previous videos that the dot product of the two vector which are perpendicular is always 0. So I can write it as a, so for example, the first equation that I will be writing is vector v minus cx. So why vector v minus cx? Because suppose this point, the shadow, the point where it ends, is nothing but a scaled version of x, and this point, okay, from which the projection start, is nothing but a vector v. So we are subtracting the cx from v, so we get the length of this line, and we are multiplying it with the vector x, that is the
the dot product of this is 0 because they are perpendicular to each other. So now multiplying vector v with vector x minus c to vector x to x. So I can write the value of c as the dot product of vector v and vector x upon the vector x dot x. So here we got the value of c. Now we will substitute the value of c into this formula for the projection. This one into this formula. So now I can write this projection of vector v on L equal to vector v dot vector x upon x dot vector x into vector x. Now we know that the value of vector v is 1, 2, and the value of vector x, okay, the x and y component of vector x is 2, 1. And same here it goes with if we simplify this, then we get here 2 plus 2 and here we get the 4 plus 4 multiply by the vector 2, 1. This will be this moment 2 to okay 4 plus 1, okay. So here we get the 4 upon 5 into 2, 1. So we are multiplying this scalar 4 by 5 into the vector 2, 1. So the answer will be 8 by 5 and 4 by 5. So this is nothing but this vector is nothing but the projection of vector v on line L or the vector x. So this point will be nothing but this vector. We have found the vector of this projection. So now we will be studying a different approach to find the projection on line L of vector v. So that is the projection of vector v on line L. So this approach will be considered as a projection as a matrix. So in order to begin with this approach, we first need to understand the two properties. Okay, so the first property is the projection must be closed under the scalar addition. So that means if I write a projection of sum of two vectors a plus b on line L should be equal to the projection of vector a on line L plus the projection of vector b on line L. And the second property is it must be closed under the scalar multiplication. So
Similarly, I can write the projection of the scalar multiplication of a vector on L must be equal to, we can take the scalar out, and I can write it as a C into projection of vector V on L. Now we will be beginning with that approach for the matrix, the projection as a matrix. So we know that the earlier formula, okay, this one, the projection of vector V on L is vector V dot vector X upon vector X into vector X, okay, multiply by vector X. So this was the formula. We know that the vector V dot vector X is a dot product, okay. So I can write this as a X transpose dot V, and similarly this vector X dot X, okay, this is also dot product, so I can write this as a X transpose dot X. So I can simplify this formula as X transpose dot V upon X transpose dot X into vector X. So I can move this, or I can like put this vector X in front of this. So this will be vector X dot X transpose dot V upon X transpose dot X. So I can write this as per the scale or the rule of the scalar multiplication. So I can write this as X dot X transpose upon X transpose dot X into vector V. So we know that the value of X and V. So if I substitute the value of X, it will be 2, 1. So this will be 2, 1 upon this will be the transpose, that is row vector 2, 1 into 2, 1, and the vector V will be 1, 2. Now we know that the shape of this vector is 2 cross 1, and here it will be 1 cross 2. So here there will be no dot product, but we will get a 2 cross 2 matrix, and in this case there will be a dot product. So I can further simplify this as this will be 4, 1 and 2, 1 upon 4 plus 1 multiply by vector having the component 1, 2, that is a vector V. So I can further write this as 1 by 5 to 4, 1, 2, 1 and 1, 2. So in this case, this is a 2 cross 2 matrix, and this is a
2 cross 1 matrix. So the output will be 2 cross 1 matrix. So this will be 1 by 5, 4 plus 2 and just a moment. Sorry, I did a mistake here. So this will be 2 into 2, 4, and the second element in the first row will be here 2. So this will be 2, and this is okay. So in this case, this element is 2 here. So it will be 4 plus 4 and 2 plus 2. So I can write this as 1 by 5 and 8, 4. So which is nothing but a 8 by 5 and 4 by 5. So using the matrix approach, we got the same value that we found earlier using this a normal approach. This value you can see. We found it using this formula. Okay. And in the second approach, we use this formula only, but we converted it into the form of matrix. Yeah. So that's it.